So this is the Physics 2-on-1 Lab 2. So our introduction, quick table of contents look here. We're going to have introduction to physics concepts, look at the tracker video and data, talk about the gravitational force only model, the gravitational drag and force model, the comparison of tracker and model data, talk about some possible sources of error, and then answer some additional questions. So for the introduction, the purpose was to observe and study the motion of a falling object, and then compare real data from tracker to two separate models, gravity and gravity plus drag. So then we have fixed principles. This is going to be Newton's second law, gravitational force and drag force. And then the outcome is we set the system as the ball and the surroundings to Earth and the air particles. In the model, with only gravity, the results do not actually line up properly. But then for drag force, when we include it, it actually does line up much more accurately to the actual experimental data. So for our physics concepts, we have the momentum principle, which is Newton's second law. And then we have the gravitational force, which, since we are close to Earth's surface, is the vector 0, negative mg 0, with m being mass and g being gravity, 9.8. And then we have drag force, which is given in the lab directions, which is f drag is equal to negative b, which is a constant which we find based on our system, and then times v squared. So for our tracker video and data, we had 21 points of data. We had an initial position with nothing in the x, but in an initial y position in the positive. And then we had an initial velocity, which we found by taking early on points and averaging them out. Change in time for my video was 0.35 seconds. And then our system is the paper ball and the surroundings is Earth and the air particles. If we look on the right, we can see X is linear system, and then we kind of see a parabola going downwards for the Y. So for the gravitational only model of the code, we have the ball mass. So this is just initial stuff that's going to be for both models. The ball mass, the position velocity vector from earlier, our time, the change in T, G, and B. For this one is 0 because we don't want drag. So that is just getting rid of that. And then, so we have our force of gravity, which is our gravity vector from earlier. I'll talk about Ft next slide, but F net in this case is just equal to Fg. And then our two kinematics equations for update and velocity, update and position. And it gives us something that looks like this on the right. And so just two arrows pointing down. For our drag force model, though, so it's the same code, except the B value actually now has a value. So if you see here, it's 0.000225, which was found by checking our model with the actual experimental results. So we keep gravity vector the same. Fd is what I was showing you earlier. It's negative b times the magnitude of the velocity squared times the ball dot vel. So we actually have the correct, we actually have it in vector form. And then we use this to calculate our Fnet in this case, which now if you look on the right, you see a small arrow pointing the other way. When we compare our data, we have tracker in blue, red is gravity only, and yellow is gravity and drag. If you notice at the end, gravity and drag and tracker both line up much closer than the gravity does. And this is because gravity is not accounting for drag force. Meanwhile, tracker does have drag force since it's in the real world in the actual experimental data. So some possible sources of error are going to be the ball measurements. The ball masses may have been measured incorrectly and not precisely enough. And the shape was definitely not spherical since it was just a paper ball rolled up. So not perfectly air resistant. The air resistance was probably not constant as well. AC running in the room or people walking by could have caused a gust of wind, which would cause this number to not always remain constant. And then tracker and precision. The video may have been recorded an angle, and the center of the mass I may have not clicked on it perfectly every single time. And then the final additional questions. First, will this actually reach terminal velocity at any point? Does any of our models predict this? Well, velocity and time graph in the y actually does, because if you see here, it's parabola. So that means at one point this will equal 0, and that is because drag force will equal gravitational force eventually. And when that equals 0, Fnet is 0. So that's going to be giving us a terminal velocity point right there. And then for the final one, if you throw it straight up with the same initial speed, will it take longer to hit the ground or will it take shorter? It will take longer because now that gravitational acceleration has to first get past the initial velocity you're giving it, since you're giving it all of the force from the x and y instead of just part of the force. And so it's going to end up increasing the amount of time it takes for it to hit the ground, since the acceleration has to first slow the object, stop it, then pull it down. And that will be the end of the video.